Okay, section 9.3, we're talking about the integral test. We have so far talked about doing a telescoping series and the geometric series test, the nth term test for divergence. So we have 3 different tests that we've talked about last time. We're going to add 2 more today. The first one is the integral test, and then from that we'll have something called a p-series. If f is positive, continuous, and decreasing for x greater than or equal to 1, and if an equals f of n, then the series, summation an, and the integral of f of x either both converge or they both diverge. We're not claiming that they converge to the same value if they converge, but they will be a relative approximation for each other, a decent approximation for each other. Now let me show you why. Notice it says positive, continuous, and decreasing. Positive means it's living above your x-axis, so you have maybe something like this. Continuous means no jumps, and decreasing means that its limit has to be headed down towards 0. That's what we're needing. Decreasing doesn't necessarily have to mean the limit is going to 0, but it has to be decreasing down. If it's an increasing function, then you're going to have an infinite integral, and there's nothing to even start with. So this is what you have to have in order to hope that your integral is going to converge. If your integral converges, then your summation converges, because remember, integrals and summations are essentially the same thing. So if I start this at n equals to 1, if you look at this, this would be f of 1 right here. So if you find the area of that first rectangle that I've drawn, its base is the width of 1, its height is f of 1, so that area for that first one is going to be f of 1 times 1, base of 1. Now if you look at this second one right here, its height is f of 2, and its base is still a width of 1. So that's the area for that one. If you keep on going, you would have f of 3 times 1 for the next one. And when you get down here to this n, you're going to have f of n times 1. So the area under the curve there is approximated by your series. And in fact, if you wanted to write it, you'd say the integral from 1 to infinity f of x dx is less than or equal to the sum n equals 1 to infinity f of n, because f of n times 1 is just f of n. And now notice I put my integral over here, my summation over here on the right-hand side. That is because my rectangles are going above my function. When you have a decreasing function, the rectangles starting on the left-hand endpoint go above your function. So I know that that summation starting at n equals 1 to infinity is bigger than my integral itself, than the area under the curve. Now, if I go and I use the other endpoint, then I will have the area for the first one right here would be f of 2 times 1. Does that make sense? And if you go with the next one over here, it's going to be f of 3 times 1, and so forth. So I know the smaller sum is going to start at n equals 2 to infinity f of n. So what we're going to do, if this integral diverges, then I know that the sum n equals 1 to infinity f of n, which is my sum n equals 1 to infinity an, because remember an is equal to f of n. This has to diverge because it's bigger than an infinite value. So it's going to diverge. On the other hand, if the integral converges, then my series n equals 2 to infinity f of n which is just the sum n equals 2 to infinity a sub n, converges. But if you add the first term to that, that doesn't change anything except what it converges to. So then the original series converges. The theorem says, if the infinite integral converges, then the series converges. If the infinite integral diverges, then the series diverges. That's our integral test. We have three things we have to verify before we actually take that infinite integral. You take the infinite integral, and the convergence or divergence of the integral tells you about the convergence or divergence of your series. You know that cheat sheet you guys have? This one needs to go on it. Yeah. No. The reason that we have the function above, well, first of all, clarify what you said it diverged. Did what diverge? Okay, yeah. It diverges because it has a bigger area than the area of the integral. So if you have an infinite area under it, then it's divergent. But the reason we need the function itself to be positive is so that you don't have any negative sums in there. Do we have our integral test copied down? Almost. Okay, I think I see most of the pencils put down. Let's do an example. Apply the integral test to the series summation n equals 1 to infinity n over n squared plus 1. So what I'm going to do is define my function. F of x is going to be x over x squared plus 1. I just replace wherever I see an n inside your series. And the first thing I need to ask you, is f continuous? In other words, will you ever divide by 0 when x is bigger than or equal to 1? No. So f is continuous for x greater than or equal to 1. You can't ever divide by 0. Is f positive for x greater than or equal to 1? Yeah. And now I have to check and see if it's decreasing. You can do it one of two ways. You can check to see if an plus 1 is less than or equal to an, or you can check to see if f prime of x is negative. We can do it either way. I'm actually going to try the derivative one because I've showed you the other one before. So let's look at the derivative. It's a quotient rule. So what's the derivative of the numerator? 1 times the denominator, x squared plus 1, minus the numerator times the derivative of the denominator, 2x, all over the denominator squared. Well, let's simplify this. This becomes x squared plus 1 minus 2x squared, all over x squared plus 1 squared. What is x squared minus 2x squared? Negative x squared, so it's 1 minus x squared over x squared plus 1 squared. The denominator is always positive. What happens when you plug in x values that are bigger than 1? It's negative. So this is less than 0 for x greater than or equal to 1. Less than or equal to 0 for x greater than or equal to 1. So it's sort of horizontal at the first value, and then it starts decreasing. So that tells you that f is decreasing. You have to verify these first three things. I'm not going to tell if you verified it on WebAssign, but I can tell if you verify it on the test after break, the test for this chapter. So make sure you verify these. I need to see this on the test. Now, what we do is we just look at the integral. I always use this starting point for my low end point of the integral, and it's also what I use for these values. So if that is started at n equals to 5, then that's what I would say x is greater than or equal to 5. So this starts 1 to infinity, x over x squared plus 1 dx. How do we integrate that? What's our first step? Before I do u substitution, I've got an infinite endpoint, so yeah, pass to the limit. Limit as a goes to infinity, integral from 1 to a. Now I can think about integrating it. So I heard u substitution. We're going to make u be equal to x squared plus 1. What is du equal to? 2x dx. So 1/2 du is equal to x dx. Plug this in. I'm going to leave off the endpoints of integration right now because it's in terms of u, and I'm too lazy to change them to u. So what do we do with that 1/2? Pull it out in front. So I have the integral of du over u. What's that integral? Not 1 over u. Yeah, natural log of u. Natural log of the absolute value of u. Back substitute. And notice that u was x squared plus 1 is always positive, so I can drop the absolute value off and plug in our endpoints. So this becomes 1/2 times the limit as a goes to infinity, natural log of a squared plus 1 minus the natural log of 1 squared plus 1. What is 1 squared? 1. Add that to 1. 2. Natural log of 2, we'll just write that. Now, a is going to infinity, so a squared plus 1 is going to infinity, and the natural log does what? Goes to infinity. So I have 1/2 of something infinite, so that's going to be infinite. The integral diverges by the integral test. The original series, n equals 1 to infinity, n over n squared plus 1 diverges. I want to point something out to you. This is not part of this example. But if you look at the limit as n goes to infinity of n over n squared plus 1, use L'Hopital's rule. You have the limit as n goes to infinity of 1 over 2n. Where does that go? 0. Nth term test from last time said, if the limit of the terms inside your series is not equal to 0, then your series diverges. if your limit is equal to 0, you know nothing. Because I just gave you an example of a series that diverges whose limit of the terms is 0. Right? Just because the limit of the terms that are being added together is 0 does not mean that it's going to 0 fast enough for your series to converge. Any questions on that? Okay. You guys get to try one. You'll see when you need that. Don't worry about it right now, but you'll eventually need that. with something like that, it's sort of a stretch. So you should have pi over 2 minus pi over 4, which means your integral is equal to pi over 4. Does that converges? So what you're going to write on your last line is by the integral test. We don't know that the series actually goes to pi over 4. We just know that the series converges. It'll go to an approximation of pi over 4, but it's not necessarily identically equal to pi over 4. Okay, do we have that one completed? P-series. This is going to be our second method. We're looking at the series n equals 1 to infinity, 1 over n to the p. That's the form that we're looking at it in. And we want to know when it converges, so we're going to apply the integral test. Question?
What if it tells us like the word tells us they both converge?
Yeah.
Does it tell us anything?
If the theorem doesn't work, it tells you probably didn't integrate it right. Because your integral will either converge or diverge, always. You don't have a case where it does something else. So, of the integral test? Yeah, if that part doesn't work, if it isn't positive, continuous, and decreasing, you have to use a different method. Yeah, I thought you were saying if your integral doesn't, yeah, but you can always evaluate your integral. Okay, so let's apply the integral test. In this case, my f of x is 1 over x to the p. And we are assuming that p is some value bigger than 0. It's not going to be negative. What I want to know is f continuous for x bigger than 1? Will you ever divide by 0 if x is bigger than 1? No. So f is continuous for x greater than or equal to 1. Is f positive for x greater than or equal to 1? Yes. And now let's look at, is it decreasing? I'm going to show you the other method. If I look at 1 over n plus 1 to the p, I want to know, is that less than or equal to 1 over n to the p? And to check that, you're going to cross multiply. So n to the p times 1, is that less than or equal to n plus 1 to the p times 1? What is n to the p times 1? N to the p? Is that a true statement? Doesn't matter the value of p actually. N plus 1 is always bigger than n. So this is true for n greater than or equal to 1, which is where we're starting. So I know that f is decreasing. I know f is positive, decreasing, and continuous. So let's look at the integral. The integral from 1 to infinity, 1 over x to the p dx. Take the limit. I'm going to write this as x to the minus p. And now I have two options. If p is not equal to 1, if it's bigger than 1, then you just add 1 to it and divide by your new power. So that becomes x to the minus p plus 1 over minus p plus 1. If p is greater than 1. If p equals to 1, you have the natural log, and you get just the natural log of x. X is bigger than 1, so I don't have to have the absolute value. Let's plug in our endpoints. Limit as a goes to infinity. We'll look at the first one. A to the minus p plus 1 over minus p plus 1. This is for p bigger than 1. So I don't have a division problem here. Division by 0. 1 minus p is not equal to 0. P is greater than 1. So my denominator here is going to be negative. The exponent here is going to be negative. So what happens is a goes to infinity to this value. Goes to 0. And then plug in our 1. You can have 1 to the minus p plus 1 over minus p plus 1. So this is a finite value. That means it converges. Let's look at the limit of the second one. As a goes to infinity, natural log of a minus the natural log of 1. What happens to the natural log of a as a goes to infinity? Goes to infinity, right? So this one diverges. So what we get for the p series is that if p is bigger than 1, this series converges. If p is equal to 1, this series diverges. Let's check and see what happens if p is less than 1. I still use the same thing. I'm going to put not equal to 1 right here. We have the limit as a goes to infinity. A to the minus p plus 1 over minus p plus 1. If p is less than 1, then 1 minus p is positive. So that means you have a to a positive exponent. What happens as a goes to infinity? Goes to infinity. So what that tells you is that it's going to converge when p is bigger than 1. It's going to diverge for values of p between 1 and 0. That is the next theorem you need to put on your cheat sheet. Copy that theorem down. This one's called the p-series. Okay, do we have our theorem copied down? So let's look at the convergence or divergence of each of the following series. State the test used. So we're looking at the harmonic series. The harmonic series, this is something you also want to remember this name. The harmonic series is the series 1 over n. I mentioned it last class period, but I told you that it diverged, but I told you I needed the integral test to show you it diverges. Well, in fact, all I need is the series test. If you look at the sum, n equals 1 to infinity, 1 over n, that tells you p has to be 1 because p is whatever is in the exponent. If nothing is showing in the exponent, then your exponent is 1. P equals to 1. Look at the theorem you just wrote down on your cheat sheet. What does that tell you? Diverges by p series. Doesn't get easier than that. Let's look at the second one. P equals to 2, converges by p series. Let's look at the third one. Yeah. So p equals 1/3, so what does it do? Diverges by the p series. You could do the integral test on each one of these and you'd have the same results. Any questions on that? You guys have one? Diverges by the p series. Why? P equals 1/2, smaller than the 1. That's all you have to do on the p series test. We like that one. That's the easiest test of them all. We are done for today. Make sure your names are on your papers and your papers are handed in.